All right, now that we have done the simulation for this parallel circuit, I'm going to show you why the numbers are the way that they are. We had a 15-volt battery attached to 3 light bulbs in parallel. The first one being 25 ohms, the second one being 50 ohms, and the third one being 75 ohms. So what you may have noticed is that the battery voltage was 15 volts, but every single light bulb in parallel got the same exact voltage. This is because each light bulb is attached directly to the positive end of the battery. I'm going to write now all of the resistances of the light bulbs. Now, when each row obeys Ohm's law. Being that I have a voltage and a resistance, I can figure out the current. So I'm going to do that for each path. V equals IR, and therefore I equals V over R. Calculating that for each path, I'm going to have the 15 volts divided by the resistance of the first path. And 15 over 25 is 0.6 amps on the first path. I can draw this on my circuit using a blue pen. We like to show little arrows that show the direction of the current flow of electrons. And we get 0.6 amps on that pathway. Now let's figure out how many amps are going to be on this pathway. Now this pathway has more resistance, so we should expect to find less current. The path still gets 15 volts, but now has double the resistance. 15 over 50 is 0.3 amps. I forgot my bracket here. Well, that makes sense. By doubling the resistance, I had half the current flowing through that pathway. So I'm going to draw a little blue arrow to show that 0.3 amps flows down through this particular resistor. And now I have my 75 ohm resistor. Here, let me complete my chart. Well, being that this one is going to be 3 times as much resistance as this path, it should be 0.2. Let's check the calculation to make sure. We have 15 volts divided by 75 ohms. Okay, plugging that into a calculator. We have 15 divided by 75. And we get 0.2. Yep, my prediction was correct. It's a current 3 times smaller than the first path. So I have even less current going down this pathway. Well, these currents came from this junction, right? Some currents going down this pathway, some down this, and some down that. That means the battery is going to have to provide all of that current. Hence, the battery current equals all the pathway currents added together in the parallel circuit. Well, that's going to be 6 plus 3 plus 2, which is 1.1 amps. Now, one would be mistaken to think that we add up these numbers to find the total resistance. Rather, we're going to use these two numbers to figure it out. Once again, I can use V equals IR, but this time I'm solving for resistance. resistance is V over I. Well, if the battery is 15 volts and it had to provide 1.1 amps of current, that is going to give us 13.64 ohms. Now, this might come to a shock to you that the total resistance is a number smaller than 25. The reason why this is the battery is providing 1.1 amps. That means the battery is feeling a total resistance that gives 1.1 amps, which we calculated to be 13.64. And I can make this an analogy to a highway system in a city. If I only had one road in the city with 25 speed bumps, the resistance of the city would be 25 speed bumps. However, if I had two roads to get to the same destination, even though that road has 50 speed bumps, because I opened up a new road, the traffic of the entire city actually went down. I can't say that the total speed bump resistance of the whole city is 75. It's going to be some number less than that. And if I add a third road, how much more so would the resistance of the traffic system get less and less? And hence, that's why in a parallel circuit, the total resistance is a number smaller than any given resistor attached in parallel. Finally, there is an alternative way to calculate this number. There's an equation in the beginning of your journal right here on the left side. It says the equivalent resistance for resistors in parallel. So let us calculate together. That's 1 over the total resistance, or the equivalent resistance, equals the reciprocals of all resistors together. Plugging that in, I'm going to have 1 over Req equals 1 over 25 ohms, 1 over 50 ohms, and 1 over 75 ohms. Now, these are 3 fractions. I can't add fractions unless I have a common denominator. A good number that would be a great common denominator would be 150. Because 75 can go into 150 twice. 3 times into 150 can 50 go. And 25 fits into 150 6 times. Now that I have a common denominator, I can add them up. 6, 3, 2, get 11 over 150 ohms. However, that can't be the final answer because my final answer is in the denominator. So continuing, I have 1 over Req equals 13 over 150 ohms. And also the ohms was in the denominator. I'm going to flip both sides. Req is going to equal 150 ohms divided by 13. Plugging that into the calculator. Oops. Let's see. We get, oh, I made a mistake. I'm sorry, it's 11 over 150 ohms. 150 divided by 11. My calculator, we get 13.63. Same answer. This was how we solved a parallel circuit.